Hello and welcome everybody. Hope everybody's staying safe and getting along all right. So today we're just going to be doing a bit of review for exam 3. And so yeah, the main announcement today is just that, exam 3 is on Wednesday, April 15th. So what is that, 2 days from now, 3 days from now? And a reminder that I will cover these 4 sections. So 3.7 was optimization and onward. We skipped 3.8 because we had a canceled week of class. We might just end up skipping 3.8. And then we'll be covering part of 4.2. So the part I want you to know from 4.2 is basically what we talked about in class and was on the homework. I want you to know how to do summations, the sigma notation and summation stuff. And then I want you to know basically the definition of the definite integral, and how to calculate definite integrals using areas, if it's a simple area, like a triangle or circle, something. How to calculate using areas. And the format of the exam will be very similar to exam 2. So I'll send it out at the usual class time. You'll have 2 hours to do it. And then it'll be due in Sakai, just like we turned our quiz in. Okay. So any questions on how the exam will work, or any other questions in general? No? Well, then let's jump right in. So I've prepared more examples than we're going to get through. So let's see. Let's maybe kind of go in reverse order. So which one do we want to do first? Let's maybe start with a summation problem. Okay, so summations, remember, are just sort of shorthand for adding up a bunch of things. And the things you add up are you plug in the various i's, starting at the bottom, increasing by 1 until you get to the top, right? So this one just means your first term would be plugging in 0, because your counting index started at 0, I started at 0. Plus 1. Then you would increase I by 1, plug that in. Right, we're taking I and we're plugging them in here, right? And then you do this until you get up to plugging I equals 3 in. So this one would be 2 squared plus 1 up to 2 to the cubed plus 1. And then you just add them all up, right? So this would be 4 plus 7, 4, 12, 13, plus 8, 24, 25, 28, 35, 49. So I got 49 when I did this. So this was the summation was a fancy way of writing 49. Okay, so that was just sort of a warm-up. So any questions about like the summation stuff? Because that, and maybe another thing about the exam that just occurred to me is because we only have like 4 sections that's covered, I expect about 2 questions a section with maybe 1 extra question thrown in. That's kind of what you should expect, roughly. Okay. So our next question. So now I want you to take a couple minutes and think about this one. This one's a little bit more involved. So here, kind of 2 notes. n is just a fixed number. It's not a variable. So n might be like 30 or something, but we just don't know what number it is exactly. It's a fixed number. And when you're computing this, what I want you to do is I want you to worry about the limit last. So try to simplify the sum using the sum formulas as much as you can first, and then worry about the limit last. Okay, so take maybe a little bit of time, see how far you can get with this. You should be able to get it down to just a number with no limits or sums. Okay. So yeah, this is a bit different than you've probably seen before. But the idea here is, and we're going to be doing a lot of this later, is let's first just look at everything inside the limit. Okay, so we can use the rule that lets us break up the sum into two parts. Like that, minus another sum. Right, remember the top and bottom numbers always stay the same as they were. Okay, and we want to get them to a place where we can use the formulas we learned last time, which is basically just if you have an I squared, an I cubed, or a constant inside the limit. And so the way we would do that is you can pull anything through a limit that doesn't involve your counting variable, your counting index. So you can pull the 4 over n squared out here. So you can take this part and you can pull it out and end up with 4 over n squared I equals 1 to n of just I. And then in the second one, I mean, really, it's already a constant already because we imagine n being fixed here, but it's probably a little easier if we pull the 7 over n out. And then all that's left in here is just a 1, because 1 times 7 over n is 7 over n. And you end up with like this. Right, and now these two sums, remember, we know formulas for them. We know if we add up the first n integers, or we sum up a constant, we can replace them with just specific formulas. So let's do that. So this would be the limit as n goes to infinity. Okay, the 4 over n is still, or 4 over n squared is still there. Then this became, you know, it was the whatever's on top times whatever's on top plus 1 over 2. So this one, that gets replaced with that, n plus 1 over 2. And then in the second one, it's just adding up the number 1 n times. So that'll just be 1 times n. So that's just an n. Okay. Now let's just simplify a little. So 4 over 2 is 2. And then the top will be n squared plus n over n squared. And then the second one is just the number 7. So you actually know how to do this limit already, right? Now it might look more familiar if I write it like this. If I just replaced all the n's with x's, it might look a lot more familiar. Okay, so what do you guys think the answer to that limit is? Because that's the kind we've done before, right? So let's get some people in chat. What do you guys think the answer to this limit is? Okay, so one person thinks -5. Any other guesses? So it turns out -5 is right. Because really what we're doing is we're splitting this up into two limits. You know, maybe it could help you if you also look at it like this even. Sorry, I copied it wrong. That might have been a little confusing. This should have been squared, right? So the limit as x goes to infinity of the constant is just the constant, right? So this part is just 7. But here, remember, like the limits at infinity, one way to quickly do them is to look at what's the largest power on the top and bottom. Here they're both x squared. And so what we do is we look at, well, what's the ratio of the coefficients if they're equal, right? It'll be 2 over 1. So this will be 2 over 1 minus 7, which is -5. Right, so it, and doing it in terms of n is the same. N is just a name for a number, though we tend to think of it as a whole number instead of it could be decimals if it's an x, but it's really the same thing, at least when you're going to infinity. Okay, so any questions about this one? So yeah, again, the idea is when you have something complicated like this, you break it down until you arrive at these limits that we know formulas for. Then you replace them with their formulas, simplify, and then use what you know about limits at infinity. Okay. Okay. And we'll be doing more of this after the exam. And then this one I'll just do quickly. So this one will not be on the exam, but I wanted to at least show you one where you have a finite geometric series. So we haven't really talked about this one, but it's such a common series that I want you to have seen it, and which is why I put 1 on the homework. And it's on the summary sheet. So the general formula is if you have a number, let's make it even easier. If I have a number, a constant, to a power, so I'm adding up maybe like 2 plus 4 plus 8, right? This would be 2 plus 2 squared plus 2 cubed, and so on, right? If I'm adding up powers of the same number, then what it works out to be is it's 1 minus the number of terms you're adding up plus 1 over 1 minus r. So this is called the geometric series. Really, this is the finite geometric series. Okay, and so the way we would do this problem using that is we would first simplify it to try to make it look like this side. So the way I would do that is I'd pull a 3 out. And you'll notice this one's a little bit different. This one starts at 0 instead of 1. There are formulas that start in terms of 1 as well, but I think this one's simpler. So this would be 1 over 2i. Well, we can rewrite that even again. This one is 200 on top. This is the same as 1/2 to the I. So really this 1/2 is our R, right? It's the number that's to the ith power. So then we can replace this part with this formula, right? And so if we do that, what do we get? Well, we still have the 3 out front, and then the sum gets replaced with 1 minus r. R is 1/2 to the n plus 1, or 1 minus 1/2. And if you want to simplify that a little bit, you can. like that'll be dividing by a half, that's times 2, so that'll be 6. Yeah. So you get some number like that. 6 times 1 minus a half to, sorry, instead of n, we should actually use our number 200. 200 plus 1. And yeah, so you get some number where it looks like it's really close to 6, right? Okay. So any questions on sums? Summation notation, sigma notation? Okay, moving on to section 3.9. 3.9 was all about, antiderivatives. And remember, the main idea of an antiderivative is, if you have a function f, its antiderivative is something else that when you take its derivative, maybe I'll just write derivative, you get f, right? So it's undoing the derivative. And sort of one of the main applications we know so far of using this is just these things called initial value problems. So we're going to do a few of those. And just for the sake of time, I might skip the first one, because I think 2 is enough to see. So we can do some other more interesting things. So let's do this initial value problem. And so, yeah, take a moment. Go ahead and think about this one. Pretend it's an exam, see if you can get the answer, and then I'll go through it. Alrighty. So maybe you didn't get it all the way through it, but let's see how it goes. So remember, the first step is to find the most general antiderivative. So you find all possible antiderivatives, so all possible things of the function r, all possible r's, because we're given the derivative. Okay, so we have to figure out which thing has derivative 2t. We could use the power rule, or the inverse power rule, whatever you want to call it. So that would be, you add 1 to the power, then divide by the new power. For the second one, you have to be a little bit more creative. There's the slight issue that there's a 3t inside of the sign. And, well, so you're looking for something that has derivative 3 sine of 3t. So you would probably guess that it's got to involve something with a cosine of 3t, right? And so if you just take the derivative of cosine of 3t, you'll see that it's minus 3 sine of 3t, right? There's a chain rule that gives you an extra 3. But we like the 3, and we like the minus sign, right? So that means this should actually just be a plus. Right, because the derivative of 3 cosine 3 is, in fact, 3 minus 3 sine of 3t. Okay, so at this point, it's still a little bit of a guess and check. But I think this one's fine. So you would find the antiderivative, you find that it's this. Let's just write it all out. Cosine of 3t. Okay, and then to make it, all possible ones could be any version of this shifted up or down by a constant c. So we have to add our plus c to make sure we get all possible ones. And then to solve for c, you use the second piece of information. So that says t is 0 and r is 5. So so r is 5, t is 0 would mean we get something like this. So 5 is 1 plus c. So if we subtract the 1 over, c has to be 4. We take that and we throw it back in for c up here, and then we get our final answer. So it's just t squared plus cosine of 3t, and then the particular constant we need to make everything work is 4. And if you're doing on these exam, doing this on the exam, it's sort of worth your time just checking everything. Like, when I take the derivative of this, do I get 2t? When I take the derivative of cosine of 3t, do I get minus 3 sine of 3t? When I plug in 0, do I get 5? And you'll see that you do. And that can be just a double check at the end to make sure you didn't make any silly mistakes. Okay. So any questions about that one? Okay, so here's one that's a little bit different. So I want you to take a few minutes and think about this one. I'll give you a hint on this one, because this one's not technically exactly like what we've seen before. This one's a slightly different type, but it's very similar. This one's technically called a boundary value problem. And you'll do it very similar, but the hint I'll give you is, normally when you're given something about the second derivative, you do the same process we just did twice. But for this one, you're not given any information about the derivative, right? Neither of these things here have primes, right? So instead, what you do is you find s right away. So take the antiderivative twice right away, and you should have 2 constants. And then plug in this extra information. Okay, so take a few minutes and think about that. Alrighty. So like I was saying, for this one, I think the easiest way to do it is to immediately go to finding s of t. But to do that, of course, we have to first do one antiderivative and remove 1 prime at a time. So the antiderivative of sine is minus cosine of t. And then we would get 3 sine of t. And then we would get a constant. That's all possible antiderivatives of s double prime. Then we do it again. So we take the antiderivative again immediately. So the antiderivative of cosine is just sine. And then you get a minus 3 cosine. Antiderivative of a constant is just that constant times the variable. And then you get another constant, which I'll call d. Okay, so now this is all possible functions s. Okay, and now we try to figure out what are these constants c and d. And so we have to use each of these pieces of information here. So let's use the s of 0, 1. So using s of 0, I would say if we plug in 0, we get 0. 3 cosine of 0 plus c times 0 plus d. So that's 0 equals 0 minus 3 plus 0 plus d. So that says d had to be 3. Okay, so that told us one of the constants. That's nice. Okay, so now what we know at this point is that s of t has to be minus sine of t. So we're sort of updating our information. We still don't know what c is, but we know that d is now 3. Okay, and then we go back up and we use this other piece of information, and hopefully that'll tell us what d is. Okay, so that says if I plug in pi over 2, I should get pi plus 2. So you end up with this equation. Let's simplify. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. Okay, so then we have like this, and then 3 minus 1 is 2. And then I can cancel the 2's. And what does this tell us? This tells us that pi equals pi over 2c. Now we divide both sides by pi over 2. So that's the same as multiplying by 2 over pi. Of course, the pi's cancel. And I'm just left with c has to be 2. Okay, and then I do one final updating of my information. We take that and we throw it in, I guess, up here. And that tells us our final s of t. Plus 2t plus 3. Okay. So that one was a little bit different, but it's sort of the same strategy in general. Is you take antiderivatives, you end up with these extra constants because you're not sure exactly what the shift was in the original function, and somehow you usually given one extra or two extra pieces of information that help you figure that out, what the c and the d are. Okay. Okay, so questions about like antiderivatives, initial value stuff? All right, so let's do another one. So here is a word problem. So, I think it's very important in math that you actually do practice, right? Practice is sort of what helps you build your mental model of how these things work, and it forces you to wrap your mind around these things. So take a few minutes and see how far you can get with this one. So this one is going to be an optimization problem. And remember, the key idea to start an optimization problem is you want to figure out what is the thing you're trying to either maximize or minimize. You want to write an equation for that in terms of the things that are can be changed. And then you want to somehow use the constraints that are given to reduce that to one variable and apply what we know about finding absolute max and mins. Okay, so take a few minutes and think about this one, and then we'll go through it. Okay. Okay, so how would I go about this one? So what I would first recognize is that, they're trying to minimize the cost. And really what you're paying for there is, you're probably paying a certain amount for each foot of length of fence, right? So you're paying per length of fence. And so to minimize the cost, we really want to minimize the total length of fence. It doesn't even look like a word. Okay, so let's write down an equation for the length. And here, in order to write down the length, it's probably most helpful to have a picture. So they said they're building a rectangular field. So we draw a rectangle. And then they said they're dividing it in two. And so I'll divide it this way. It doesn't really matter which way. And we could build this in various shapes. It could be long and skinny, or tall and skinny. So the things we really have control over are like the length and width, or length and height. So we want to give those some variable names because they can change. So maybe I'll call this side, I guess we'll do it y because it's vertical. And then there's many ways you could do this, but I'll choose to call this length x. You could also choose to call the whole bottom x, and it'll work just as well. And so now if you do it like this way, then the total length of fence is, you have each of these black lines is made up of fence. So you have to count the total length there. So there's 3 y's, and then there's how many x's? There's 1, 2, 3, 4, right? We're doing this just in half, right? Divided in half, yes. This is the right picture. So this would be 3 y's plus 4 x's. Okay, so we want to minimize this, but we have a problem because there's 2 variables, right? So in order to be able to actually have just a single answer, there has to be some sort of constraint. Otherwise, there's many possible answers. And so the other piece of information we're given here is that we want the area to be 6 million square feet. So that's our constraint. So a million has 6 zeros. It may seem like a large number, but areas are squares of things, so it's not actually that big. So our total area has to be 6 million square foot. But in terms of x and y, what is this area? Well, the length of this thing, or maybe the width, is 2x, right? It's 2 x's on the bottom. And then the height is y, right? So the total area would be like this. And we want to solve for one of these variables so that we can replace it up top, right? So, you do whichever one you think is simplest. I might solve for x maybe. So x will be 6 million over 2y. So that's 3 million over y. I'm going to take that and I'm going to put it back in for our L up here. Okay, so let's do that. So that'll tell us that our L, in terms of just one variable now, just the variable y, it was 3y plus 4x, and x is this thing. Right? So let's just simplify that. That's 3y plus 12 million over y. Okay, so that's the thing we want to minimize. And so to minimize, right, we usually find the critical values by taking the derivative. So let's take the derivative, would be just 3 minus, so the derivative of, a number over right? You can think of this as like being like 12 million times y to the minus 1. So its derivative is negative 12 million y to the negative 2, which is also same as having a y squared on the bottom. And we want this to be 0, right? And to solve that, I would probably take one of these terms to the other side. If we do that term, it makes it nice and positive. Lots of zeros here. Bring the y over here. So that would say 3y divided by 3 now equals 4 million. And this will just be in terms of feet, because y is a length. Okay. And so this is a possible answer, right? Whenever we find these critical values, it's never for certain that this is the answer, but often it is. But we should always check. So we want to check that this is a min, because it's possible it could be a max or a neither type. Oh, good point. I didn't get rid of the square. Thank you. I dropped a square. Yeah, there is supposed to be a square root in here. So yeah, y should be the square root of this. Thank you. And if you were getting the square root here, you would technically get like a plus or minus. But because we obviously will only care about the positive length, we just take the positive one. Okay, and so if we think about this, this is really like the square root of 4 times a million. And a million is 1,000 thousands. So this is 2 times 1,000, which is 2,000. Right, which is probably easier to see the other way, right? If you square 2,000, you'll get 4 and then an additional 3 zeros. So yeah, this is in terms of feet. Okay, thank you. So yeah, this is a more reasonable amount of feet, right? We probably would have realized this eventually, that we had done something, we had missed something, right? Because our number was way too big. And then yeah, what we were doing is we wanted to check that this is a max, or sorry, a min. So we're trying to minimize the length. Minimum, and the way we do that is you could either go through the whole process we did before by checking endpoints. So maybe it's not entirely clear what the endpoints are here. I think you could actually figure them out. But an easier way would be to use the first or second derivative test. And because we haven't used it that much, I'm going to go ahead and use the second derivative test, because it's also easy here. So the second derivative test would say that if we take L double prime, so if you look back up, what was L? L was 12 million, it was this thing. So the derivative of 3 will be 0, and then the derivative of the other one will be, you'll get an extra factor of 2, because it's like y to the minus 2. And then you'll get an extra plus, or an extra negative to make it plus, and then you'll get the 12 million over y cubed. So overall, you should end up with 24 million over y cubed. And if you plug in the critical value we found, this is positive, right? Okay, so if the second derivative is positive, this means L is concave up near y equals 2,000 feet. Right, so the idea is, right, concave up means it's here. The place where the derivative was 0 is here. So this was a min, right? So this is a technique that works. It's a local min, but because there was only one critical point, right, our endpoints are like over here and over here somewhere. So, the only way this could have happened is if this was actually the absolute min. Okay, so then our answer is really this. Y equals 2,000 feet is the correct one. Let's make sure we answer the entire question. So it was asking, what should the lengths of the sides of the rectangular field be? So that probably means it wants this, and it also wants this. So the field should be, so that means we need to know what x is. So x here is, if you go back up, we had a formula for x in terms of y right here. X equals this. So if you plug in the y you found, or was it 6 or 3? 3. And then y we found was 2,000. Okay, so the field should be 2 times this, because it was 2x was the total width, by, so this amount of feet was our 2x, by, maybe I'll just write the word by, y was 2,000 feet. And I think this simplifies, right? You could cancel a 2 and cancel a bunch of zeros. So it's 3,000 by 2,000 feet. Okay. Okay, so any questions about this one? All right, if there's no questions, we'll move on to this one. So we're not going to get through everything, of course. But I might just show you how to do this one. This one's a fairly quick, if you know how it works. So basically what it's saying is you have an object, it's moving along a straight line. And you know that after 10 seconds, so at t equals 10, you know 2 pieces of information about it. You know that its position is 500. So so S is, right, so remember, S is the position. S prime is the velocity. And S double prime is the acceleration. Okay, so the first thing they told us is that it is accelerating at a constant rate of 10. Right, so here, so that would tell us that at all moments in time, the acceleration is just a positive 10. And then at t equals 10, its position is 500, so that says that S at time 10 is 500. And we also know that its velocity at 10 seconds is 300 feet per second. So that says the velocity, s prime, at time 10 is 300. Okay, and so if you put these all together, it makes up an example of one of these initial value problems. So it turns out with this information, you can tell how the object moved at all moments in time. So you put it all together, the IVP you get is, you know this about the derivative, that it's equal to 10. It's not a 10. You know that its velocity at time 10 was 300, and its position at time 10 was 500. Right? And then it just, so that would be the modeling the situation as an IVP. And then we just solve it like before. So to solve it, you would take the antiderivative. So S prime would be 10t plus some constant. Find the most general antiderivative. And now we know something about the derivative, so we can use that immediately. This is a little bit different than the other one we did, right? The other one we weren't given information about the derivative. But if we use this, this says that 300 equals 10 times 10 plus c. If you solve that for c, right, 10 times 10 is 100, c is 200. Throw that back in. It's 10t plus 200. So now we know that the velocity at all moments in time was this equation. Then you repeat the process once more, right? You would take the antiderivative. So the antiderivative of t is t squared over 2 plus 200t plus another constant. And I'll call that a different constant d because it might be a different number. And then we use this other piece of information that if I plug in t equals 10, I get 500. So this is 5 times 10 squared plus 2,000, 200 times 10, plus d. This lets us figure out what d is. Let's see, 500 minus 500. D is minus 2,000. And we put that back in our S. Plus negative 2,000. And this will be in units of feet, right? Okay. Okay, so any questions about that one? Okay, so let's, I want to try to hit the most important ones before we end class. But I will post solutions to these so that you can see them. So let's look at this one. So this question is basically asking us to, so we learned about these things called definite integrals. And here we want to calculate what they are. And so we know, well, actually, maybe it's better if we do this other one first. Right, so what do we know about definite integrals. We know basically two things about definite integrals. We know sort of one, they represent areas under functions. That's one of the most important things. And the second thing is their definition. Okay, and so the first thing, or I mean, this question is asking about the definition, right? So the definition is that it's the limit as, if we approximate a function by a bunch of rectangles and then we take the number of rectangles and send it to be really huge, off to infinity, then we get the exact area. So, this integral stands for the exact area. And if we wanted to actually calculate it, we have to do this kind of horrible limit of a sum thing, right? So remember, the definition is that an integral from a to b, this is going to be our definition of any definite integral, the way we would calculate this area. So this would be the area of under f of x between a and b, is you send the number of rectangles to be really huge. So n, not x. N is the number of rectangles. And then you divide your interval 2 to 6 into a bunch of pieces. And the width of each rectangle is b minus a over n, delta x. And then you add up all the heights of the rectangles, right? Because each one will be the width times the height. And so that'll be you just, and we're going to stick to right endpoints for this definition. And so that's always you take the starting bound, the lower one, plus, then you move to the right by delta x each time. And so you end up with this. Okay, so this is the most general definition. And if we just plug everything in here, what is delta x here in this particular problem? It's b minus a over n. And then here, b is 6. 6's and b's look like the same thing. So it'd be 6 minus 2 over n if we're using n rectangles. So that'd be 4 over n. And now I throw everything in here. So the integral from 2 to 6 of x minus 2 cubed, and, maybe it's worth, this part here, let's just figure out what this is. So b minus a over n was this, so this would be, and a was 2. Okay, so the first thing we do is we write the limit. And I'm just copying this limit thing, but I'm plugging in all my numbers. And then b minus a over n was 4 over n. And we have our sum. And then f is this part, right? This is f of x. So we have to plug this in for x here, right? And when we do that, so instead of x, we write 2 plus I times 4 over n. And then, so this was x. And we had the minus 2, and then we had the cubed. Right, because we're plugging this in for x in f, and f was x minus 2 cubed. And if you simplify that a touch, you end up with this. So the 2's cancel here, and it's just the sum of 4i over n all cubed. So this would be the definition. So if we wanted to actually calculate this exact area, you kind of would have to go through this process, right? Which we saw an example of sort of how to do this earlier today, one that was sort of similar. And that's what we'll be doing after our exam is like, so I expect you to know how to write this down right now, but I don't expect you to calculate it all the way through. That's what we'll get to after the exam. Okay, but you should be able to write down the definition, right? So this is the definition, and you should be able to plug in your your delta x and your right endpoints, and end up with some mess that looks like this at the bottom. Okay. Okay, so then the last thing I want to talk about today is the other thing you have to kind of know about this stuff is, you know, these definite integrals, they stand for areas. And so I expect you to be able to calculate them if they make certain nice shapes that we actually know the areas of. If there's some other weird shape, you probably can't do it yet, but we'll get to that after the exam. But here's an important one. So this would say we want to find the area under this function between -3 and 0. So you might think, like, I have no idea what the area under this thing looks like, but if we call that the function y, and I square both sides, and then I move this, just kind of rearrange things, and I'll write 9 as 3 squared. So this is the shape of a circle, right? Circle of radius 3. So this is something we can do, but we have to make sure we get the right part of the circle, right? So if I look at what I had, so I really had this thing, square root of 9 minus x squared. And if we're thinking of that as giving the y value, this will always output a positive number. So this right here is it's not the whole circle, it's the top half. Right? If you wanted the bottom half, it would be the negative version. This would be the bottom half. Because a circle isn't actually a function, right? So it actually has multiple pieces. But so here what we're working with is the top half. This is not what we want. So if we draw a picture now, just draw a crappy circle. So let's imagine we have a circle of radius 3. We wanted the area under the top half, just the top half, between -3 and 0. So -3 is over here. So really that just means I want this part. Okay, because it's between -3 and 0, and it's only between the top half and the horizontal axis. So it's really just a quarter of a circle. So the area is a quarter of a circle. And we know the equation of the area of a circle is pi r squared. We know the radius is 3. So overall, you get 9 pi over 4. Okay. So some of these you can do just by sort of understanding what they're trying to calculate, if they're a nice shape. And basically the only ones I expect you to know right now are circles, things that involve triangles and squares and circles, yeah. Okay. All right, so any questions? That's gonna have to be about it for today. We do have our drop-in office hours if you wanna ask some questions about like the exam practice stuff tomorrow. We'll be around. Yeah. Other than that, there will be no class on Wednesday, right? Just you be taking your exam. Other than that, have a good day, and I'll talk to you on Friday.